Hi, everybody. I just wanted to check in and go over a few things from last week. Sorry I can't be here again today. I'm still taking care of my son. Hopefully I'll be back tomorrow, which is Tuesday. So in this unit, I wanted to look at Earth's temperatures because Earth's temperature is very important because it actually provides us with liquid water. So other planets and moons and places in the solar system, the galaxy and beyond, have water, but we have something special in liquid water, and it's Earth's temperatures that provide us with this liquid water, which is the main ingredient we found for life. So we have not found life on Earth that doesn't need liquid water. So when we go out into the solar system and the galaxy and the universe to look for life, what we actually look for are places, planets, moons, that have temperatures that could possibly have liquid water. And also, we want our Earth to continue to support life. So we need to make sure it continues to have the conditions to have liquid water. So we're going to dive into Earth's temperature. Okay, so first I had you look here and make a prediction about which planet you would think would be the hottest and the coldest based on its distance from the sun. And most people had said that Mercury, they thought right here, would be the hottest planet because it's the closest, and Neptune would be the coldest planet because it's the furthest away. And based on our life experiences, generally when we are close to something, you're warmer, and when we're further away, you're colder. But as we look at the data, we find that's generally true, but not always. So if we look here at the data, I don't even know how I did that. I'm just trying to look at this here. We can see, so as we look here at the data, so we have here the order from the sun, so the different planets. I'm trying to get this to right on here, but for some reason, there we go. We have Mercury, Venus, Earth, Mars, so we're moving further away from the sun here, and the temperatures plotted. And we can see here that Venus is actually the hottest, even though it's the second from the sun. And Mercury's temperatures, average temperature is about right here. But actually Mercury does get very hot, but it also gets very cold. There's places on Mercury that get colder than planet Earth. And then we can see here, it says Saturn is the coldest. Well, and actually this isn't very true. It's actually Uranus gets some of the coldest temperatures, and Neptune is the average coldest. But this graph was pretty organized, so I kept this information. But you can see the general trend as you move away, again, let's say this is the sun, is that the temperatures do on average generally get colder as you move away from the sun, with exceptions like Mercury not being the hottest, and Venus, and then with some kind of temperatures down here. So following that, I had you brainstorm some possible other factors that could affect the temperatures of a planet. And a lot of you came up with things like color and atmosphere and the speed of rotation, which are all very possible. And if we think about it like the color, if you're wearing a certain color, sometimes you feel warmer or colder. Does that happen in a planet too? Or let's say, you're sitting around a campfire and you have a jacket on, right? You're going to feel warmer than, if you don't have a jacket on. So whatever surrounds you, which would be like your atmosphere. So what we're going to look at with this unit is, how can color affect the temperature of a planet or a moon, and how can atmosphere, all right, your jacket or your blanket affect your temperature? Nope. So looking into color, if we want to figure out how color affects the temperature of something, we first need to figure out what is color and what are you seeing when you see color. So here I had you look at something called radiation, and the sun gives off lots of different types of radiation, and that's energy given off in waves. And the sun gives off lots of different types of radiation. So radio waves, microwaves, infrared, visible. And this is the visible light spectrum right here. This is what we can see with our eyes, and we see them as the rainbow color. Ultraviolet, X-rays, gamma rays. All different types of radiation. A wave of radiation has a couple factors that we need to kind of look at. And the top of the wave is called the crest. So here are the two tops of the waves. And the distance between two crests right next to each other is called the wavelength. And the wavelength determines a lot of properties about that type of radiation. So it determines what kind it is, if it's a color, an X-ray, a gamma ray, that different type of thing. So when we look down here at different colors, we can see colors are different wavelengths of radiation. And you can see here that we have red, and this has the longest wavelength. And then as we move through the rainbow, red, orange, yellow, green, blue, indigo, and violet, your Roy G. Biv, you can see that these wavelengths get shorter and shorter and shorter. Right? And when we're actually seeing different colors, what we are is seeing the different wavelengths. So why do we see different colors? Well, white light is actually all the rainbow, the Roy G. Biv, moving really, really fast. Right? And as that white light hits different objects, some of the color is reflected. So reflected is to bounce off of something. And then other wavelengths are absorbed into that and then transferred into heat energy. So what we have here is white light. When you see something white, it's all the colors of the rainbow moving really fast, and it hits an object and it bounces off and it comes to hit your eyes. And you see that as white light. If you're looking at something that is black in color, what you're actually seeing is that the white light hits the dark color, and then all those wavelengths are absorbed and transferred into heat. And it looks dark because nothing is bouncing off of it and coming to hit your eye. So then why do we see different colors? Well, when white light hits something, and let's say blue, and I don't think I can change the color here. All right, so blue bounces or was reflected off, all the other colors are absorbed, and then the blue light, that blue wavelength actually hits your eyes, and then you see something the color blue. So whichever color is being reflected is what you see. So here you have white light hitting an object and green bounces off. Right, so now you're going to see the color green. I wish I could change the color of this. Right, or when you see something that's the color red, that means red light is bouncing off the object, and then all the other colors are absorbed into that object. So depending on the color, different amounts of light are going to be absorbed and reflected, and whatever is absorbed is going to change into heat. So that is going to heat something up, and that is going to get warmer. So this leads us to a phenomenon called albedo. And albedo is the measurement of how much light an object reflects. Okay, so if something has a high albedo, that means it's reflecting lots of light. So here is the high number right here. So let's say this is, radiation from the sun coming in. It hits it. So things that are light in color reflect a lot more. So a lot of that light bounces off, and this object is going to be cooler, right? Because not as much radiation is being absorbed and transferred into heat. So something with a high albedo is typically cooler, while something that has a low albedo, darker in color, that solar energy hits it, and most of it's absorbed, right? And therefore it is transferred into heat. And this will generally get warmer. All right, so this has a low albedo or a low reflection, and that is going to be something that's darker, right, and gets warmer. And something with a high albedo is generally lighter in color, and that's going to be cooler if everything is the same. So today I would like you to look at albedo and see how that affects the temperature of Earth. So just simply changing the color, how that can either heat up or cool down the Earth depending on how the color is changed. So this is just looking at some of Earth's surface materials. So if something absorbs a lot, it's going to be dark and it's going to reflect very little. And then again, the lighter in color it is, the more light is being reflected and the cooler it will be. So then if I could have you here, just put down, and you can arrange these and move these, which you think has the lowest albedo, so that absorbs the most. And then over here, the highest albedo, which of these surface materials of Earth would have the highest albedo. Then you can move through and check your answers and put in your responses.